Good morning. I have the honor of opening up the data track by talking about data without actually showing you any data, so that's going to be fun. This talk is not necessarily about the history of data science, but it does have some connections with the history of science, and I think that can be relevant for data science also. The title and the content of this presentation has changed quite a bit. So apologies if it's not exactly what you expected based on the description. But let's get started. My name is Lukas Vermeer. I'm a product owner at Booking.com. Booking.com is the world's largest accommodations provider. It's one of the best kept secrets of Amsterdam, I guess. It's sort of the elephant in the e-commerce room. No one seems to understand exactly how big is. We're one of Google's biggest customers. In fact, when I asked Google if we were still their biggest customer, they said, "Oh yeah." So we're pretty big. I'm responsible for experimentation at Booking.com. So when we make changes to our website, we want to know if people actually like it. Of course, we do usability studies, we do lab studies. We ask people if they like it, but there's no alternative really for just trying it out in the real world and seeing whether people respond to your change. And so we run web-scale experiments where we make changes to our website and see how people respond. And we have infrastructure in place to do this, and that's where I come in. So it's partially tooling, partially training, a lot of speaking, a lot of telling stories. Statistics is sometimes a difficult subject for people to grasp, but I find that if you tell stories, it's much easier to understand. This talk is not necessarily about sauerkraut, but there will be sauerkraut. Let me start by saying, start this story by telling you about this ship. The HMS Endeavor sailed out of Plymouth on the 6th of August in 1768. And this ship had two missions. One was public and for the good of science, and one was very, very secret. In fact, it was so secret that the captain of the ship didn't know what the mission was. He was given an envelope and told that once he had completed his first mission, he would be allowed to open up the envelope and read his instructions. Now, if you try to be a data scientist about this and said, well, let's just look at the data and see whether we can figure out what these guys are going to do, and you dig up the ship manifest, and the ship manifest tells you exactly what is on board this ship. And you look at the manifest, and one thing really sticks out, is that along with all the other things that they would usually take on a voyage like this ship is also carrying 3 tons of sauerkraut. Now, I don't know about you guys, I like my fermented cabbage every once in a while, but 3 tons of sauerkraut is a lot of sauerkraut. So in this talk, I want to challenge the idea that this was actually helpful, that having all the data is useful. I want to challenge the idea that in big data, all you need is a lot of data and a smart data scientist, and you can figure everything out. And in this sense, data, or big data, is a little bit like sauerkraut. You can have a lot of it. If you don't know what to do with it, okay, so maybe that analogy doesn't quite work, but we'll see where we get. The talk is divided into 3 chapters, and chapter 1 is on revolutions. Maybe not the kind you were thinking. So Thomas Kuhn wrote an interesting book and he's on the progress or the scientific revolutions, and he says a very interesting thing. He says, progress in science is not a simple line leading to the truth. And I say this to people, and they say, yeah, I know that. It's more like a meandering river that flows towards the truth. I said, no, it's not like that at all. Science makes regressions all the time. It's not the exception, it's the rule. It steps forward, does 1 step back, 2 steps forward, 1 step back. Science is not a simple progression or a simple line leading to the truth. It's with jumps and starts and movements back and forth. I think a very interesting example of this, if my clicker actually works, is, see this clicker? It's huge. It's the biggest clicker I've ever seen. It's awesome. It's like ancient technology. So Aristarchus of Samos was a Greek philosopher who lived 3 centuries before Christ. And he had this interesting idea. He said, if you're going to build a temple, and the solar system is the biggest temple I can think of, then what any god would do is put the light at the center of the temple so it illuminates all things. Now, for a Greek philosopher, this is a pretty good argument. These days, we would hardly accept that as evidence. But he hypothesized for the first time that the stars were fixed and far away, that the Earth was revolving around the sun rather than the other way around. And this was widely accepted in his time. People around him thought this was a fair point. You know, if I build a temple like that, I would put the sun in the center. And so this was accepted theory at that time. Now, it's very weak evidence, right? There's no data here. He has a model. He has reasons for believing that the model is correct, but he has no data to back it up. So along comes this guy, 200 years or 400 years later, Claudius Ptolemy. He tried to sort of summarize the ideas of the ancients. He tried to summarize all the theories that the Greeks had, and when he came to reason about the solar system and what exactly lies at the center, there are really 2 competing ideas at the time. One, the sun is at the center of the thing and everything revolves around the sun. So that's a heliocentric model, helio being the sun. But there was also the geocentric model, which is the Earth is fixed and at the center of things and everything revolves around the Earth. Now these can't be true at the same time, so Ptolemy has a problem. He has to figure out which one is true. He wants to summarize things. And he says, you know, this notion that the Earth revolves around the sun is altogether absurd. It's crazy. Because if the Earth were in fact revolving around the sun, for us to have day and night, the Earth would also have to spin at the velocity of one revolution per day. Now, 1 revolution per day, they had a pretty good estimate of the size of the Earth at the time, so they calculated how fast the Earth must be moving. And he said, if the Earth is indeed spinning this fast, then anytime I throw something up in the air, the Earth will outstrip it, and so it should fall to the west. This is brilliant thinking right there. So, I mean, if you throw it up, the Earth will spin underneath it, and then stuff falls to the west. Great, you can run an experiment, try that out. And so what he said was, I don't observe this westward motion. I don't see this. It's not happening. Also, if the Earth was actually moving, the stars should be moving relative to each other because of movement. Just like you're in a car and you see a tree in the house, they move relative to each other. It's called parallax motion. And this was also not seen. The stars are fixed. And this is a third key point. They had mathematical models based on the idea of geocentricity that allowed them very accurately to predict where the planets that they could observe were going to be the next day. So they would say, I know where Mars is going to rise, I know where Venus is going to rise, and I'm using this math that is based on this idea that the Earth is at the center of things, and so I have no evidence that the other thing is true. In fact, I have 2 things that I should have observed, but I have math that supports the other thing, QED, quote erudum strandum, therefore it is proven. But what he actually means, and this is the key thing here, is that both of these first 2 points are an argument from absence of evidence, right? What he's saying is, I have no observed westward motion, no observed stellar parallax, and I have geocentric math that works to explain what I have actually seen. And these things are key because this westward motion does actually exist. It's called the Coriolis effect. And it took about 2,000 years before they actually got to observe it. When they started shooting cannonballs, these cannonballs fly so far that you have to start to correct for this effect. And so this effect that he's talking about, that he's using as evidence here, does actually exist. But he couldn't observe it because the effect is too small. And the same goes for stellar parallax. So stellar parallax is real. It does exist. What you need is very good equipment to be able to observe it. But it does happen. And so basically, it's not QED, it's GED. Good enough, dude. Right? With what I have observed now, this works. So along comes this guy, about 1,000 or 1,500 years later, and he says, hey guys, I read this awesome book by this Greek guy called Aristarchus, and he has this great idea that, in fact, everything revolves around the sun instead of everything revolving around the earth. Now, finally, when he prints his famous work on this thing, about his Revolutions Omnibus, he conveniently leaves out the fact that he got this idea from some ancient Greek. I don't know, maybe there weren't enough pages or something, but when he published it, that little detail got lost. And one of the interesting objections to this model at the time was that this model, although we now think this is simpler because it doesn't require all of the counter-revolutions that were needed in the geocentric model, one of the objections was that why is the Earth the only one that has a moon? Everything revolves around the sun except for the moon. This model is not simpler, it's more complicated, right? And so, interesting thing in the foreword that was written by, so this was published only on the year of his death, right? Copernicus was quite fearful that it would be misconstrued as something against the church. And so did the person who wrote the foreword to his book, and said, these hypotheses need not be true nor even probable. On the contrary, if they provide calculus consistent with the observations, that alone is enough. Now, this is an interesting way to think about scientific models. They don't have to be true as long as they help you predict what's happening in the real world. I'm not sure I agree with that point of view, but it's interesting that Seander wrote this under a pseudonym. Actually, he used it. He didn't even want it to be known that he was the guy who wrote the foreword for the book. So that's how crazy they were at the time. Still, there's very little evidence, actual evidence, that this is the right model. This was not accepted when Copernicus wrote it down. People said, no, we have the geocentric math, it works fine. Until this guy comes along. And this guy is not, in any sense of the word, a philosopher, right? The real breakthrough that led to the acceptance of the heliocentric model was not a philosophical or theoretical breakthrough. It was a technological breakthrough. This guy built telescopes. That's what led to the acceptance of the heliocentric model, because he built the telescopes that were better than anyone else had ever constructed, and this allowed him to observe for the very first time moons around Jupiter. And this is when people started saying, wait a minute, if this other planet also has moons, then our geocentric math suddenly becomes a lot more complicated. Because now we have to correct not just for this backward motion we seem to be observing on the planet itself, but also the moons around it seem to be, moving with it. So we need a more complicated model to make that work. And this is what finally led to the acceptance of the heliocentric model, because that actually makes this a lot easier to accept. But it's this observation made possible through better telescopes that finally led to the acceptance of the heliocentric model, almost 2,000 years after some guy said, if you have a light, put it at the center. And the key thing here is that there's always multiple models that can explain the data that you already have. So you have a bunch of data, you look at it, you go, here's a way I could explain this data. But if you have multiple models, then the way to find out which model is correct is usually not found in the data you have, because that's the data you use to come up with the models in the first place. And so it requires a concerted effort to actually collect new data, usually to the contrary of one of these models, to prove that one or the other is correct. So this brings this notion of having two types of data. There's the data you have. You probably have lots of it, and that's okay. You can have lots of it. And there's data you need. And they don't necessarily completely overlap. In fact, very often they only overlap a very little. And in case it wasn't abundantly clear, that's the sauerkraut, and that's the science, right? This is the stuff you have that you really don't have a need for. And then there's a lot of data that you actually need that you don't currently have. And thinking about this is what the scientific method is all about. That, to me, is what data science is all about. Chapter 2. Transit. So we talked about revolutions, let's talk about transit. Aristarchus wrote lots of things, and most of it was lost, but the only thing that was really preserved was on the sizes and distances, where he tries to estimate the size and distances between the heavenly bodies that he could observe. So he tried to find how far away is the sun from the Earth? How many Earths could you fit between here and the sun? Now, he's doing this using very simple geometry. It's actually quite nice. If you finished high school, basically, you can do this. So you don't need any university degree. It's super fun if you're bored. And so what he's using is things like the solar and the lunar eclipse to try to estimate in a geometric model the distances between the planets. And he comes to this number. And so this is somewhere between 380 and 1520. And this uncertainty isn't his. He wrote down a very definite number. But the unit of measurement he used was a stadi. And the challenge with this is that depending on inflection, this can mean very different distances. And the work was transcribed several times, and so we don't know which one he meant. It's like as if the word meter could actually describe a meter and a kilometer, and depending on whether you say meter or meter. And so this wasn't preserved, and so we don't know if he actually meant 380 or 15 and 20. So it's somewhere in that range. If he meant 15 and 20, he's off by 1 order of magnitude, approximately. So it's not so bad for a Greek philosopher 300 years before Christ. And so about 2,000 years later, along comes Mr. Halley, yes, from the comet, Halley's comet. And he wrote an interesting dissertation. He said, if we were to observe how Venus moves across the sun, we can use very similar geometric math to calculate more accurately the distance between the Earth and the sun. And the way this works is you try to observe from different places on the planet when Venus, which is a tiny speck compared to the sun, when Venus starts transiting the sun and when it ends. And when you have these different observations from different parts of the planet, then you can estimate the parallax. So you can estimate the triangles between the sun, the Earth, and Venus, two of them. And this allows you to then estimate distance. Now, what you would need for this is observations of Venus crossing the sun. And luckily, this had happened about 6 years before the HMS Endeavor left Plymouth. And that wasn't accidental. This ship was actually going to Tahiti. Because they figured if we can make this observation from England, let's go find some other place on the other side of the world. So we can make the same observation. We can also see the transit of Venus. So James Cook, who's the captain of the ship, sailed from Plymouth all the way around South America to Tahiti and back the other way for 2 timestamps. So forget big data for a moment. This is big. Like he's actually sailing around the world for 2 timestamps. But they're very important timestamps because these 2 timestamps should allow us to calculate how big the solar system is. Now, James Cook gets to Tahiti on time, which is good because otherwise they have to wait another 200 years. So, so he gets there, and the weather is good, so that's awesome. No clouds. And so they could actually see Venus move across the sun, so great. But there's a problem. They had 3 people on Tahiti making the same observation, and they got to very different numbers. And the reason was that once Venus starts crossing the sun, there's an effect called the black drop effect, where the backlighting of the sun causes it to appear as if Venus is merging with the edge of the sun. And this makes it very difficult to say when does the crossing actually start. And so the 3 people making observations in Tahiti disagreed more than they would have liked. So the margin of error was a lot bigger. So they were at the right time, right place, right idea, just an insufficiently accurate telescope. Bummer. Luckily, Jerome Lalonde, a few years later, could still use this data to estimate the distance between the Earth and the Sun, and he came to about 24,000 Earth radii, which is about 2% off. So it's not, the real number is like 23,400 and something. So it's not too bad. It's actually pretty good, considering they thought the mission was a failure. So the key here is that science is limited by the data we can collect, and that data is actually limited by engineering more than you think. And so if you think about doing good science, it's not just about having the right idea. I mean, Aristarchus had the right idea about the heliocentric model, but it took 2,000 years for them to actually be able to collect the data that they could use to prove that this model was correct. And here, what happened to James Cook is that they actually had the right model, the right place, the right time, but then they didn't have a telescope that was accurate enough to make the actual measurement. So you're still limited by engineering. I think Elon Musk put it very well in an interview. He said, in the absence of engineering, you do not have the data, you hit the limit. You can be real smart within the context of a limit of the data you have, but unless you have a way to make more data, you can't make progress. And this is key. If you work only with the data you have, you're never going to make progress. You have to think about the data you need to create in order to progress. So this brings us back to this model, where there's data you have and data you need. And I think what's often overlooked is that both of these are dwarfed by the data you could create. If you think you have a lot of data now, just think of all the data you could create. Now, I'm not suggesting you should, because storing all of that is going to be a nightmare, and most of it is going to be useless. But it is useful to think about the data you could create as opposed to the data you have and the data you need. We'll come back to that later. First chapter 3, transmutation. This brings us to alchemy. So this really irks me. This rattles my nerves when people write stuff like this. When people talk about data science, often they're using analogies that are worse than using sauerkraut. They talk about data as the new oil, the new crude, the gold to be found, the nuggets to be dug up by some mythical data scientist that's going to find it for you. And this, to me, is not science. This is alchemy. Just before the scientific revolution, many of the people who were also chemists were also alchemists, and one of the things they tried to achieve was this philosopher's stone, this legendary substance that would allow you to turn lead into gold, or crude into oil, if you will. And I think a lot of the rhetoric around data science is very similar in this sense, that it doesn't matter what kind of data you have, just bring a data scientist on board and they can turn it into something really valuable. To me, this is the data science versus data alchemy dichotomy. And a good example of this is Kaggle, your home for data science. Kaggle is a website where companies can put data sets and questions, and data scientists or machine learners will come and try to solve them. But the way this works is that as a company, you have already defined exactly what the problem looks like. You have already defined exactly what the data looks like. You've already defined how the data is collected, how it's stored, how it's encoded, and you also decided what the output is going to be. All that's left to do is the translation from one to the other, from the input data to the output data. So this leads to a very peculiar kind of thinking, where if you give people a challenge like this, so people who are used to the Kaggle way of thinking, if you give them a challenge to say, well, we have a bunch of hotel reviews on this website, Booking.com for instance, and we want to show something good, something bad. We want to show what's good about this hotel and what's not good about this hotel. Now, if you ask someone who's accustomed to the idea of receiving data as is and then thinking about ways to turn it into gold, then they will come up with something like this. Sentiment analysis, formulas, try to find out whether you can find the words that are key that tell you what the sentiment of the sentence is. This is very hard because humans use irony and sarcasm and humor, and those things don't translate very well into computer speak. So Kaggle to me is Kaggle to me, real machine learning is like chess is the war, right? It's an interesting mental exercise. It's probably part of the entire thing, but it just isn't everything. The large part of the struggle is actually figuring out what data you need to collect, how to collect it, how to encode it, and what the output is going to be. And so if you give a challenge like this to what I would call a data scientist, they would come up with something like this. You give people 2 boxes, and one box you put a smiley face on it, and you say, what did you like? And the other box you put a frowny face on, and you say, what did you not like? accuracy 99.9%. This is better than any algorithm can ever give you, because we get all the positive sentiment in one box and all the negative sentiment in the other box. It's almost perfect. We solved the problem at data collection stage. And now I hear you thinking, this is too easy. Yes, it's too easy. Is that a problem? So, thinking about the data you create, or you could create, is actually useful because it makes many problems a lot easier. I want to walk through a few of these to give you an idea of how this model could be used. So, if you have data that you have, but you don't need at the moment, but you could also never recreate it. Do you delete it, or do you archive it? So that's a tough decision, because if you delete it, you can never get it back. The same is not true for the data you have, you don't need, but you could recreate, right? So I have some data. If I really needed it in the future, I could recreate it. So then can I delete it? Well, what's the cost of recreating this data? That's versus what is the cost of storing it? So now it's obvious that these two types of data are very different, in the sense that I have to think about how I would use them. On the other side of the spectrum, and this happens a lot in my world in experimentation, is there's data I need, but I don't have and I cannot create. I would really like to know, when we run experiments on Booking.com, I would really like to know whether people love it. Sadly, I can't put probes in people's brains and figure out whether they love it, because that'd be not nice. And so we have to find proxies for the thing I actually want to know. But it's good that I know that what I need I cannot get, because then I know why I'm looking for proxies. And I realize that the things I'm using are actually proxies for the thing I can't get. So here's an example of some of this stuff being applied at Booking.com. We wrote a paper for KDD. Thanasis and Mats did. I wasn't involved myself. I only reviewed it. But I think it's an interesting application of data science. So we wanted to send out an email that says, does this sound like you? Our team of travel scientists have thought long and hard about your next holiday, and based on your past adventures, they think you have a passion for, and then we'd come up with reasons that you go on different trips. Now, to do this, you need some past places people have gone to, but you also need to know why they went there. And so one way to figure out why people go to a particular place is to let me skip to that, is to scrape Wikipedia, but you can also just ask them. So we asked them, why did you go to Willingen? I didn't click any of the boxes, because none of the reasons were actually in Willingen. But so we sent out this email that suggests these things are relevant for you. And so some people loved it, and some people really hated it. Like, you should probably fire your team of travel scientists. Hard to be more wrong. And so the cool thing here is that we look at this and we go, well, that's qualitative data, right? It's not quantitative. I mean, the uplift is there. This totally worked. So the first email campaign is sending out this thing. All the numbers. Like in science, if something is significant, you make it bold. So all the numbers in our paper are bold, because sample size. And so it was a really very, very successful email campaign. And then this feedback comes in where people say, well, yeah, it's hard to be more wrong. You should probably fire travel scientists. And some people even thought it was creepy. Because they thought a human was looking at their bookings, because it says travel scientists, right? This is people. And so we sent out the second email campaign. This almost doubled the impact of the entire thing. And I do this presentation at conferences for machine learning. And people asked, what parameters did you tune? Did you change the model? Is there a new data feature that you fed into the thing? Have you figured out a smarter way to? No. We took out 2 words: travel scientists. People thought it was creepy, so we replaced it by something that didn't suggest a human had looked at their bookings, and we doubled the impact. Right? So this data is very valuable, because it tells you something about what users perceive when they get this thing. And if you have a data scientist that only thinks within the context of the data that they have to build the model, they're never going to figure this one out. And so double the impact, remove 2 words. So deciding what data to collect and how is a fundamental step in the scientific method, and it's limited both by theory and by engineering and by humans. You have to have the right people to think about these things. I think if there's one slide you remember, it's this one. So some of us are philosophers. Some of us come up with a theory, like Aristarchus. And it doesn't even have to be well-founded by data. Theory, as long as it's somehow disprovable, that's good enough. And some of us will build telescopes. And I think at a conference like this, you're more likely to be telescope builders than philosophers. But do not underestimate the importance of your role. If you say, well, I just do data collection, right? That's the easy part. No, it's not. That's the hard part. At scale, that's difficult. Counting is hard. Rounding errors are problematic. Floating point is tricky, right? Good data collection is really, really difficult. And so don't underestimate the importance of that in relation to the data scientific method. So when I do interviews, I live and die by this. I judge a man by his question rather than his answers. I give a data scientist a problem. If they solve it, that's nice. If they ask questions that make me think, that's a good one. That's one I want. So with that, questions? Do we have to pass the mic? Does someone ask a question? Yes?
I got one other question in the app, and it's sending out recommendations email are not very critical to be actually correct. Do you use data science for actually critical decisions where you can't afford being wrong?
So an example of where you can't afford to be wrong. Financial transactions, I wouldn't use this. I wouldn't use an experiment there. But we use experiments for pretty much everything. So even infrastructure changes are run as controlled experiments. I think, so one thing is, can you afford to be wrong? And the other is, can you afford not to know? So if you make a change and you say, well, I'm going to make this change, but I'm not going to run an experiment on it, I'm not going to validate that this is the right thing by having a good control, then you're essentially saying, I don't care if I'm incorrect about this thing, and that it doesn't improve the metric in the way I thought it was going to. And that's okay. I mean, if you think the risk is greater. How much, do we have time, or?
Yeah, we have a couple of minutes left, so if there are other questions as well.
So my job at Booking is to tell stories, right? And I call these statistical stories, so I have one that fits here. So two statisticians are hiking in the woods. It's always about statisticians, these stories. And you can imagine the types, right? They've got big wellies, pants up to here, big glasses, bit nerdy. And so they're hiking, because that's what they want to do in their spare time, and it starts to rain. And they don't like rain, so they start to look for shelter. And in the distance, they see a cave. And so they run up to the cave, and the first statistician says, I'm going to go inside to check if it's safe. So, okay, second guy stays outside. First guy goes in, rounds a corner, and about 5 seconds after he rounds the corner, the second guy standing outside hears a loud roar, and something that sounds like ruffling of a big hairy beast. And then silence. Now, the second guy standing outside is a statistician, so he says, look, that was not a representative sample of statisticians. It also wasn't a very large sample size. I didn't have a control. There might be lots of confounders going on, but I'm not going inside. Because if there is a bear in there, I don't want to know. And so when you ask, like, do you have decisions that are too risky? Oh yeah, yes. But then you decide between knowing and risk. And you say, this risk is so great that I don't want to know. I don't care, I'll stand outside, I'll be wet. That's okay. As long as you know that's what you did. Yeah, good point.
Okay, we've got time for one question left, so if it's one. Otherwise, thank you.
No one asked about sauerkraut. I have all these slides.
Yeah, there were questions, what is sauerkraut, but I think...
What is sauerkraut? So sauerkraut is fermented cabbage. So it's a German dish. I have 5 minutes? Awesome, I can do my slides. I'm
1 minute left.
I'm really disappointed in you guys. Like I put this teaser in, 2 of them actually, and no one asks, because I have another one. The cook brought sauerkraut because scurvy was a disease that was plaguing the ships, where your teeth start to fall out and you die. It's not great. And they had some idea that it might be caused by lack of fresh fruit and vegetables, Actually, one of the first experiments ever, Lind, he gave a few sailors fresh fruit, and it totally worked. Too bad they ran out of fresh fruit real quick. It's hard to bring fresh fruit on a boat. And so they thought, maybe if we bring sauerkraut, that'll work. So they brought 3 tons of sauerkraut to feed it to the sailors to see if that would cure the scurvy. And it turns out Cook didn't have a lot of scurvy on his ships, but it wasn't because of the sauerkraut, it was for other reasons. So again, difficult to make a good reading. And scurvy is a good example of science making these regressions again. So as I was researching this, every time I look at scientific progress, I find these regressions. In the case of scurvy, the English Navy figured out that you had to eat limes, sour fruit, and you wouldn't get scurvy, so awesome. Then in the 18th century, ships got faster, and they went to India, and they found that the Indian limes were actually cheaper than the Mediterranean ones, so they ran an experiment swapping them, and they found no difference. So they said, well, let's use those. And the reason they found no difference because by then the ships were so fast that no one actually got any scurvy anyway. They were eating limes for nothing. And by the 19th century, someone wanted to go to the North Pole, and figured out that they were going to get scurvy along the way. This is probably bad. So we should do what the Navy does, and they brought lime juice, and it didn't work, and they all got scurvy because there's not enough vitamin C in the Indian limes. They hadn't figured out that it was vitamin C yet because you need a very, very, very good reading. It's a very small molecule, and so they rejected the idea that it was these limes that helped fight scurvy. So they had the right model. They actually had a solution. Then they tried it out, and they were like, oh, wait, this doesn't work. They rejected the entire thing, and they went to a model where they said scurvy is caused by a disease in meat that's not fresh, which is entirely wrong, but that's the model they adopted. And then in the 1950s, that's when they finally were able to detect vitamin C and said, wait a minute. Actually, it's a deficiency illness. It's caused by lack of vitamin C, and that's when they rediscovered the fact that these fresh fruits help against scurvy. So it's another example of science going, yeah, I gotta go, oh, no. And again. And this happens all the time. It's very...
And thank you, Lucas.
Cheers.